work joint with my beloved wife, Sharare, who happens to be the computer scientist of two of us. I'm a mathematician by training, and theoretical computer science for me is more mathematical challenge than real application. So if my talk is a little dry or simple-minded for the computer scientist community, I apologize in advance. And also, she happens to be much more eager than me to attend this conference, but unfortunately, due to the new regulations of Trump, she couldn't get visa to come to the US, so I'm giving the talk instead of her. So this is going to be about improvements on the kCenter problem for uncertain data. First, I'm going to introduce the problem in the classical setting, and then I'll make it into the uncertain for the uncertain data, and I review some of the literature about this, and I'll give some results that we have found and explain the proofs if I have some time. The slides doesn't happen to be in the, there is something. So how does it do? Full screen? Oh, thank you. Okay, so the classical kCenter problem is something about clustering. It's very well known. You have endpoints that are clients, and we want to build K servers and locate them such that it's very convenient for these clients. So that means that we have to define some sort of cost, the hardship for these clients to go to these servers, and minimize it. So each client goes to the closest center to it, and we want to minimize the maximum distance that the client travels. So that's the cost. This simple problem happens to be NP hard because a lot of problems in graph theory, like domination, can be reduced to it, and they're known to be NP complete. So we are happy if we find an approximate solution. By that I mean that a solution that its cost is not minimum, but it's at most alpha times minimum. So it's alpha is the constant for approximation. So for this classical problem, there is a two approximation that is very simple-minded, very naive, and was found by Gonzalez. And it's very fast. The time for this algorithm is O of n log k. N is the number of clients, and k is the number of servers. And this naive approach actually is the best one for a general metric space. It is shown that if P is not NP, then one cannot find any 2 minus epsilon approximation solution for a general metric space. But if you're working in a Euclidean space, things are much better. For any epsilon bigger than 0, one can find a 1 plus epsilon approximation, and that running time, if you assume that k is fixed, is linear in D and N. D is the dimension of the space. So what we want to do is that we replace the certain data points to uncertain points because, for example, the clients don't have a fixed location. They might be in different places randomly with different probabilities. So each point, instead of being fixed, has z different positions, like pi1 up to piz, and there are given some probability distributions. And we also assume that these probabilities are independent from each other. Of course, one can put different models. For example, instead of having a discrete set of locations, you can have a continuous set of locations, or the distributions could be joined. We didn't study these things, but they have been studied in the literature. So now with the cost, we have to define some sort of expected cost. So depending on how you define these expected costs, there are different versions of this uncertain problem. So the unassigned version is the simplest one. So for each realization of these points, you find the cost of the centers C relative to that realization, and you take the average, weighted average of all these realizations. So I want to actually emphasize that even calculating this cost requires an exponential amount of calculation, because the number of summands is equal to z to the power n, where z is the number of locations of each random client. So our goal is now to find a set of points C such that this expected cost is minimized. One can have an assignment. So suppose these clients, there's people in a city and these servers are hospitals. So each person doesn't necessarily go to the closest hospital to it in different realization. It gets assigned to some sort of hospital. So we have an assignment that for each random point pi assigns a center. And now instead of finding the distance between a client to its closest center, we find the distance between that client in its realization to an assigned center to that person. So this is the expected cost. And now in the unrestricted version of the problem, we're not just producing CIs, we're also producing an assignment that makes this minimum. So among all different centers and all different assignments, give me the minimum one. In the restricted version, however, the assignment is specific and is fixed, and we want to find the centers relative to the assignment. But the assignment has to be given in some sort of, it has to be a rule that I'm going to explain. It's not completely random. So there are 3 assignments that we use in our work. They're called expected distance assignment, one center assignment, and the expected point assignment. I'm going to explain them briefly now. So in the expected distance assignment, each random point gets assigned to a center that has closest expected distance to it. So the expected distance between a random point and a certain deterministic point Q is this weighted sum that I have written. So now, regardless of the realization, each point is assigned to a fixed center. In the one center assignment, so we take the one center of a random point pi, and I denote it by pi tilde, and actually find a center that is closest to this one center. So if you have forgotten the definition of one center, is a point Q which has the minimum expected distance to pi among all the points Q in the space that you're dealing with. In the expected point assignment, this only works for a Euclidean space. For each point, you define a pi bar, which is the weighted sum of these realizations. And adding points is legal in a Euclidean space because it's a vector space, so you can define this pi bar. And each point gets assigned to a center that is closest to this expected point. So now let me tell you a little bit about the work that has been done previously on this area. The notion of kCenter for uncertain data was studied by Cormode and McGregor in a paper in PODS in 2008. They produced some approximation solutions, but this is a bi-criteria approximation, meaning that the cost is not exactly optimum, is up to alpha times the optimum cost, and also the number of centers is not exactly k. They can produce more, but up to a constant factor. And then later on, Guha and Munagala improved onto, in this result and made the number of centers fixed and still found a constant factor approximation solution, which the constant factor is 15 times 1 plus 2 plus epsilon, 2 times epsilon. So in our work, we have decreased this number to 10, and in later work, we have actually decreased it to 6. So we have a 6 approximation solution for the unrestricted assigned version for any metric space. Okay, so there are some other work. Let me go fast on these things. Okay, so I'm going to present the results of our paper in a series of theorems. However, these theorems are not very abstract. They have a flavor of, they actually can be applied and be treated as algorithms. So the first theorem is about a set of clients in a Euclidean space. So assume that P1 up to Pn are given in a Euclidean space and define as before the expected point P1 bar.
Just a quick question. How's the input distribution specified?
So the input distribution, each point has a certain set of locations as Z location, and each location has a probability assigned to it. And these probability assignments for different points are independent from each other. So for P1, I mean a set of points, P11, P12, P13 up to P1Z, and each of these points have a certain given probability. So by P1 hat, I mean the realizations of P1. So there are Z possibilities. So that sum is over all these Z possibilities. So this theorem says that if you take the expected point of any of these points, no matter which one, say P1, this is going to be a two approximate solution for the one center problem for P1 up to Pn. And it's very good because the time for finding P1 bar is equal to the number of possibilities of P1. For example, it's O of Z. So it doesn't matter how many points you have. So regardless of the number of points, you can find a two approximation solution for the one center problem. Now, if you're working in a general metric space, now you can't find the expected point. This theorem tells you that instead of looking at the one center all over the space, you just think about the different realizations of P1. So if you just have one uncertain point and you're trying to find the one center of this one uncertain point, you look at all its possibilities that it has. So there are Z possibilities, and you see which one of them give you the best solution. And that is going to be a two approximation for the one center for P1. If the number of points is more than one, there are n points, you just take the point that was from the previous theorem, but this time it's not going to be a two approximation, it's going to be four approximation solution for this set of n points. So it's almost as fast as the previous theorem for the Euclidean space, but it's like Z squared, so because you have to check for all these different, n times, Z squared for 1 point. Okay. Now, the next result is about, so remember when I told you about the restricted and unrestricted assigned version of the kCenter problem. So it says that if you take the expected distance assignment and find the kCenter for this assignment, maybe the expected distance assignment is not the best optimum assignment possible, but it's not worse than 3 times the best approximation, the best assignment. So the expected distance assignment for a general metric space is usually very closely related to the best approximation. Actually, we conjecture that it is the best assignment for many cases. Actually, we did some calculations. In many cases, it is the best assignment. So the next result is, again, for the case when you're dealing with a Euclidean space. The difference between the Euclidean and the general metric space is that usually the constant factors that appear in the approximations are better. So in the next theorem, I'll give the same theorem for the general metric space, and you see that the numbers are a little bit larger than these. So remember when I talked about the classical version of the kCenter problem, it's a very old problem, and there are a lot of algorithms that give you 1 plus epsilon approximations in the case of a Euclidean space. So our general idea was to change these uncertain points to certain deterministic replacements. So each uncertain point gets replaced by something deterministic. So the very naive idea is that to replace each uncertain point to its expected point. So if you do that, you have now a classical kCenter problem for P1 bar up to Pn bar. And suppose you find an approximate solution for its kCenter, C1 up to Ck. And now you can ask yourself, okay, what could this solution in the case of the uncertain data? And what we could prove is that this solution, when you calculate the expected cost of it with the expected distance assignment is not more than 5 plus epsilon times the optimum cost. And when you take it using the expected point assignment, it's not more than 3 plus epsilon times optimum cost. So of course, now it shows that for the Euclidean case, it's better to take the expected point assignment rather than the expected distance assignment. So now, if, for example, you take the greedy algorithm that I mentioned at the beginning that gives you a 2 approximation, in that case epsilon is 1, and you get a very simple and fast algorithm to approximate the expected distance assignment version of the uncertain kCenter problem with a factor of 6, and the expected point version with a factor of 4. Okay, finally, when you're dealing with points in a general metric space, so you don't have the expected point associated to each point. So what you do, you replace these PIs with their one center. So P1 tilde, P2 tilde, up to Pn tilde. But even the one center for a single uncertain point is NP hard, so you can't calculate it exactly. So what we do, we find an approximate one center. So suppose the approximation factor is 1 plus delta. So we replace these P1 up to Pn with the 1 plus delta approximation solutions for their one centers, P1 prime, P2 prime up to Pn prime. Now we have transformed the problem from the uncertain situation to the classical situation, and we have some algorithms to find their solutions. And suppose the solution is C1 up to CK. And now this solution is going to be an approximate solution to the best possible solution, and the approximation factor is what I have written in the slide. It's 1 plus 2 plus epsilon times 2 plus delta. Usually in the general metric space, one cannot do better than a 2 approximation. So both delta and epsilons are 1, and that gives me a 10 approximation solution for the general metric space. This OC prime that I have written is for the assignment related to the one center. So each point gets assigned to a center that is closest to its one center. But since the one center of a point is not exactly calculated, we want it to be closest to its approximate one center. That's why I have written a prime there. Okay. Now, in this table, I have written all these results in terms of the speed, the running time, and also the approximation factor. So RD stands for the Euclidean space, the d-dimensional Euclidean space, and general means that you're dealing with the general metric space. The last line actually is the most general result that we have. In the general metric space, and if you want to solve the unrestricted assigned version of the kCenter problem, you can do it with an approximation factor of 10. And the running time is not that bad. It's O of nk plus nz squared. N is the number of clients, Z is the number of centers, and Z is the number of locations that each random point has. Okay. So I want to also tell you a little bit about the flavor of the proofs of these results. And since they're working with for general metric space, we use triangle inequality in a metric space to prove it. The first lemma actually tells you why it is different in a Euclidean space than in a general metric space. These expected point P bar that I defined has this interesting property that the distance of P bar to Q for any point, deterministic point Q, is always less than or equal to the expected distance between P and Q. And if this property holds for a general metric space, I mean that for any point, random point P, you can define as an axiom a point P bar with this property, then a lot of results and approximation factor that we had for the Euclidean space get transferred to that that particular type of matrix space. So in order to prove, for example, this lemma, you take the distance between p bar and q. So I've written there the definition of p bar. It's the sum, the weighted sum of p hats. And then since the sum of the probabilities of p hats is 1, I can write it in the way that I have written there. And then once you use the triangle inequality, the result follows. So it's very simple. So I'm going to skip these results, the proofs that I had here, because I don't have too much time. I just go to the conclusion. So the main observation that we had is replacing the uncertain points with this clever choice of a deterministic point. And this clever choice for a general metric space, it's one center or an approximate one center. And for a Euclidean space, it's expected point associated to it. And then show that this, when you solve this classical problem, you get a good approximate solution for the uncertain problem. And in the future, we want to study the other variants of the cost function, for example, k-median that appeared in the previous talk, or the k-mean. And also, we want to study the unassigned version for a general metric space. All the results that I said was for assigned version. The unassigned version, we didn't talk much in the paper, but we are trying to do the same approach for the unassigned version of the kCenter problem. Okay. Thank you.
So about the definition of problem, probably you mentioned. So for kCenter, there are actually two versions, right? So you first, like kCenter is like a max, and then max and sum, the sum and max. So if you change these two operators, it's different.
So instead of taking the max, I could have taken the sum of all the distances, or take the sum of squares. These, but I don't think I can switch the order of min, max,
so
and
I think in the previous paper by Guha and the others,
they take the sum, I
they
think.
consider two versions, right? So one is called per point, like kCenter per point, the other is kCenter global. So if you basically first take the expectation of the sum, and there's a sum of the expectation. So,
Oh, yes, yes.
The max, not
Right.
yeah. So which version you considered here?
I take the, for each realization, I calculate the cost, and I take the average for those realizations with the weight. The expected of each cost. So I take, for each realization, I find the cost, and then I take the average of all these costs.
How about the other version?
We didn't study that.
Oh, okay.
A quick question. So in the proof, moving from Euclidean to other general metric spaces, if you use only triangle inequality, that does not...
So the only difference is the existence of this expected point that we have for the metric space. So in the metric space, we always have, for a random point p, we have a point p bar that is deterministic, and the distance of p bar to any other point is always less than or equal to the expected distance of p to that point. If this happens to be true in that metric space, then those proofs go through.